Let's solve problem 2 from the spring 2025 second midterm exam for physics 151. You can see a projection of the problem down here. In this problem, positive charge Q starts out at rest and it enters region 1, which has no magnetic field, but which has some unknown potential difference between the two ends of this region. And as a result of that electric potential difference, it gains some given speed, v1. So it goes from v initial equals 0 to v1 is a given value. The charge is given, it's the proton charge. The mass is given, it's the mass of a carbon-12 ion. The particle then enters region 2. In region 2, we're told that the electric field is 0. The magnetic field is for us to determine. And in that magnetic field, the particle executes a semicircular orbit of radius r, where r is given. We need to determine the magnitude and direction of the magnetic field in region 2. We also, I think, need to determine the particle's speed as it exits region 2. Then the particle enters region 3. The magnetic field in region 3 is to be determined, direction and magnitude. The electric field in region 3 is to be determined, direction and magnitude. But we are told that on the left side of region 3 is a conducting plate of given area. And on the right side is a conducting plate of given area. And there's plus Q here on the left side. There's minus Q here on the right side. The value of Q is given. And this separation D is given. So we know this area, we know this separation distance, we know this charge. We need to determine the electric field. We need to determine what magnetic field would cause this particle to go through in a straight line, undeflected. So there's quite a bit to unpack there. Let's take it piece by piece. Okay, just reading the problem aloud, a carbon-12 ion of charge Q equals plus 1.60 times 10 to the minus 19 coulombs, and mass M equals 1.99 times 10 to the minus 26 kilograms, is initially produced at rest with V0 equals 0 at the bottom of chamber 1. Okay, so that is right there. It is accelerated by a potential difference, delta V, that's capital V for voltage, not little v for velocity or speed, and it emerges from chamber 1 with velocity, v1, lowercase v1, is 4.50 times 10 to the 5th meters per second. There is no magnetic field in chamber 1. It then enters chamber 2 with a uniform magnetic field, B2. This is a constant magnetic field, always in the same direction, but we don't know the value, we don't know the direction. But no electric field, E2 equals 0. It follows a clockwise circular path of radius r equals 20.0 centimeters. It then emerges with velocity v2. It then emerges with velocity v2 directed downward. So this is straight down, minus y direction. It then passes through the plates of a parallel plate capacitor of plate separation D is 3.00 millimeters and area A is 0.250 square meters that holds charge Q equals 3.00 microcoulombs. It is observed that this ion moves through the capacitor in a straight line. Part A. What is the potential difference, delta V, capital delta V, in chamber 1, and which side of the chamber, upper or lower, is at higher potential? So we know that we can write electric potential energy as charge times electric potential. So charge times voltage is electric potential energy. So I can say that the energy initial equals energy final. So 1/2 mv0 squared plus this charge times v initial. This is at the bottom. Actually, I'm going to call this V bottom, that's where it enters, equals 1/2 mv1 squared, there's the final velocity, squared, plus q v top. This term is 0, so I think I want to solve for v top minus v bottom. So I can say v top minus v bottom equals, so there's top, this comes over here with a minus sign, this goes over here with a minus sign, so this is mv1 squared with the minus sign divided by 2q. So this is delta V. You could choose your own sign convention for delta V, but then the question is which side is at the higher potential. So I think the bottom has to be at the higher potential so that you get a positive kinetic energy here at the end. You see, so Q, which is positive, so it's a positive charge. So V bottom minus V top equals 1/2 mv1 squared, which is a positive kinetic energy. So V bottom is bigger than V top for a positively charged particle. So this, we can work out a number, and the potential at the bottom is bigger than the potential at the top. So next, for part B, we want to know what is the direction and magnitude of the magnetic field B2 in region 2 to give us this given radius r equals 20 centimeters for the positively charged particle bending around clockwise like this when it enters this region with speed v1 with velocity directed upward. So if we have just a magnetic field and no electric field, then the speed should be constant. The magnetic field will change the direction of the velocity vector, but a magnetic field will not change the magnitude of the velocity vector. So the speed will be the same v1, which is 4.50 times 10 to the 5th meters per second the whole time. Now, when I look at this, I want to find a force, a magnetic force, which will be toward the center. So the magnetic force has to point to the right when we first enter this region. So here's F magnetic. That's not the field, that's the magnetic force on a positive particle. And then I guess as a check, we could say, well, the magnetic force on a positive particle has to be downward when we're kind of halfway through this orbit. So we know that the magnetic force is QV cross B, and upon first entering region 2, we have V is V1 in the y direction, the plus y direction, and we want F magnetic to be in the plus I hat direction. We want it to be in the plus x direction. So let's try a magnetic field pointing out of the board. As the magnetic field points out of the board, then V cross B will actually do what we want. Aha! This is my right hand, by the way. It looks like a left hand in the reversed video. So QV cross B would point to the right if B points out of the page. I think we can try, so let's try B2 is some B2 magnitude times K hat. That means out of the board in the plus Z direction. Then QV cross B is QV1 J hat cross product with V2 K hat. That is charge times speed times magnetic field magnitude times J hat cross K hat, and J hat cross K hat equals I hat, K hat cross I hat equals J hat, I hat cross J hat equals K hat. Swap any two of these, you get a minus sign. You notice this is just cyclic permutation, so this is IJK, IJK, IJK in order from left to right. Another trick is you can just keep writing. So then IJK, JKI, KIJ. Those are all plus 1. And if you have to permute a pair, that gives you a factor of minus 1. So this is QV1, V2, I hat, which is what we want here, because I hat points toward the center when we first enter. We could just do a quick check what happens when we're at the top here. So at top of semicircle, we have V is same speed, but now we're in the plus x direction, so that's V1 times I hat. So QV cross B is our magnetic force, so that would be Q, and then here's V1 I hat, and then the magnetic field is still going to be B2 K hat. So this is Q, V1, B2, those are all the coefficients, and then I hat cross K hat. See, I hat cross K hat is minus J hat. I hat cross K hat is minus J hat. Okay, so this is QV1 B2 minus J hat. That's good. That's what we want, because when we're at the top of the semicircle, we want this force to be downward. So that's good. Okay, so that's a good check. Then, how big a magnetic field do we need to make that happen? Okay, now we want to express the fact that the centripetal force, the force bending this particle in a circle, is the magnetic force. So the centripetal force is mv squared over r, where the speed here is this given value v1, and that equals the magnitude of the magnetic force. So this is the magnitude of QV cross B, and this magnitude just equals, well, we can just write Q since Q is bigger than 0, and this is V1 and this is B2, and we can just write these magnitudes like this because we know that V1 is in the XY plane and we know that B is in the Z direction, so they're perpendicular, so there's no sign factor. So now we can simply solve for B2. So the magnetic field in region 2, B2 is mv1 squared over r divided by Q be 1, and that is mb1 over, here we can write absolute value of Q R. So we know Q is bigger than 0, so the absolute value is superfluous in this particular case, but in general, the relationship between the momentum in the numerator here, the radius of curvature, and the magnetic field and the charge would involve this absolute value. Then we can plug in numbers and we get that the magnetic field in region 2 is 0.280 Tesla out of the page, which is the plus z direction, which we label with k hat, the unit vector k hat. Now, for part C of the problem, we want to know what is the speed v2 as it emerges from chamber 2. Well, there's no electric field in region 2. An electric field would change the particle's speed. A magnetic field does not change the particle's speed. It only changes its direction. So the speed is still 4.50 times 10 to the 5th meters per second here at point 2 when it leaves region 2. But now it's going downward in the minus y direction, whereas it was going in the plus y direction when it entered region 2. Okay, now, part D, what are the directions and magnitudes of the electric and magnetic fields in region 3? So this is basically a parallel plate capacitor. So we want to figure out the electric field inside a parallel plate capacitor. And then we want to figure out what the magnetic field has to be such that the electric and magnetic forces together sum to 0, so that this particle just moves in a straight line. If there were an electric field in this downward direction, then the particle would speed up. Or an electric field in the upward direction would slow it down for a positively charged particle. We know from studying parallel plate capacitors that the electric field goes from the plus charge to the minus charge, so the electric field points in the plus x direction. We're going to ignore any little issues with the field lines, so-called edge effects, so we usually assume that a parallel plate capacitor is large, so that in the entire region of interest, the field lines are parallel. You know, in real life, near the edge of a parallel plate capacitor, the field lines would bend a little bit, but we're going to ignore those so-called edge effects, and we'll just treat the electric field as being entirely from left to right here, from positive to negative charge, which is a legitimate thing to do if this capacitor is much wider than the plate separation. So the plate area, we're told, is 1/4 of a square meter, so that's like 1/2 meter by 1/2 meter, and this plate separation is like a few millimeters. So that seems reasonable. This plate is much wider in these two dimensions than it is in this separation dimension. So we can treat the electric field as uniform. So in this region 3, the electric field lines will be like this. So E3 is some magnitude times I hat. It's going to point to the right in the plus x direction. And if we want to, we could use Gauss's law to figure out the electric field, or we could just remember the result. There's kind of a bunch of different ways we could get it. One is to remember the result that the electric field in a parallel plate capacitor is sigma over epsilon naught. And sigma is charge per unit area. So that gives us the given value Q, and then we have the constant of nature epsilon naught and the given area. Another thing we could do is we could remember that a parallel plate capacitor has capacitance equals epsilon naught times area over distance. And then we could remember that Q equals CV, so the voltage is Q over C, which would be charge times separation distance divided by epsilon naught A, and then we might remember that the electric field in the x direction is minus the derivative of the electric potential with respect to x. So that gives us that the potential difference is the magnitude of this electric field in the x direction times this plate separation. This is also a given equation on the equation sheet, that potential is electric field times distance for a uniform electric field. So if we did that, then we would get that the magnitude of the electric field is just this voltage difference divided by D, which is the same result. So here's the charge divided by epsilon naught times the area. So there's several ways you could get that. You could also get it from Gauss's law. We could make a little Gauss's law surface here. I could make the area of this thing be little a, and I could make the area of this thing be little a. So the electric field is 0 over here outside of the capacitor, and the electric field lines are parallel to this surface, so that dot product in Gauss's law would be 0 here, and it's 0 here also. So the only place I get a non-zero electric flux is this surface. This surface has area little a, and electric field, unknown electric field E. So I would say that the electric flux is the electric field times this little area A, and then that equals the enclosed charge divided by epsilon naught, and the enclosed charge is sigma times the area, and then sigma is just the total charge in the capacitor divided by the area of each plate. So this gives me that the electric field is sigma over epsilon naught, which is what I wrote down up here. So then that leads us once again to this result. You could just pick whichever one of those few methods comes to mind first to get the electric field from the charge on each plate, the area of each plate. Okay, now electric fields can change a particle's speed. Magnetic fields cannot change a particle's speed. The electric field is always perpendicular to the velocity, at least for our intended path, where the particle travels in a straight line downward. So the particle will travel at constant speed, and it's traveling in a straight line. So traveling at constant speed in a straight line corresponds to 0 acceleration. That corresponds to 0 net force. So that tells us that 0 is the electric force plus the magnetic force. So that equals QE for the electric force plus QV cross B for the magnetic force. And we can factor out the Q. So in fact, we just want to have V cross B equals minus E to get this factor in parentheses to equal 0. And so we just worked out the magnitude of the electric field. So this is minus E3 in the I hat direction. And the velocity is V2, which is the same as V1 actually, in the minus J hat direction. It's going downward, and then cross product with the magnetic field. So what direction of magnetic field would get us that result? So we have velocity cross some magnetic field direction. We want that cross product to point left. So here's velocity. We want the result to point left. Velocity cross product, magnetic field pointing out of the board. So here's the velocity downward, magnetic field pointing out of the board. That would give us V cross B pointing left, which is opposite the electric field. So that should work. So we have the magnetic field is some magnitude times K hat, which is out of the board. So this will be B3 K hat. So this equals V1, which is the same as V2, which we want to be the same as V3, and then V3, and there's a minus sign. And then we can do the unit vector stuff, J hat cross K hat. So just to make sure we copied this correctly, V1 minus J hat, V3, K hat. J hat cross K hat is I hat. So this is minus V1, V3, I hat. So that can work as long as this is in the minus I hat direction, the minus X direction. This is in the minus I hat direction, the minus X direction. This works if E3 equals V1, V3. So that gives us B3 equals E3 over V1. So then the desired magnetic field is 3.01 Tesla in the K hat direction. That's pointing out of the page. So here's B3 pointing out of the page with this magnitude. It might not hurt to do a check. So you might want to just think about the fact, positively charged particle, QE is the electric force, that will point to the right. QV cross B is the magnetic force, that will point to the left. So we got the directions correct. And then we can check that the magnitudes are the same. So 3.01 Tesla times 4.5 times 10 to the 5th meters per second should equal 1.36 times 10 to the 6th volts per meter. And sure enough, the calculator says that works out. So I think we solved this whole problem. So the electric field in region 3 is 1.36 times 10 to the 6th volts per meter, pointing to the right. And the magnetic field in region 3 is 3.01 Tesla, pointing out of the page. This little box here in region 3 is known as a velocity selector, because if the particle had the wrong velocity, suppose it's moving too slowly, then the magnetic force would be too small, it would get deflected to the right. Suppose it's moving too quickly, then the magnetic force would be too big, it would get deflected to the left. And in practice, what you do is you put a little iris down here. So when it gets to the bottom, it goes through a little collimator or iris, so that only particles that are in this narrow range of speed can get through.